All right, so we're talking about a problem, and you may remember this. This is a problem that talks about the sitting back to knee length for a group of adults. Um, so, if you're sitting on a chair, for instance, I think what we're talking about is this distance, back to knee length. All right, and so what we know about that is that it has a mean of, in this case, 22.7 inches. And it has a standard deviation of 1.1 inches. All right. So we use this data, like it says, to design different kinds of seats. And so what we want to do is instead of using 0.05 for identifying significant values, use the criteria that a value x is significant if the probability of being greater than it is less than 0.01, and the probability of being less than it is 0.01. So in other words, what we're doing is we're finding the probability that, well, let me draw a picture. That's probably our easiest way to do this. They're saying, okay, normally in a normal curve, we would define these two boundaries. Oh, thought I lost it. These two boundaries as being critical, okay, and the what would make them critical is what's significant about those boundaries is that the area is of being greater than that or less than that is 0.05. Okay, so the probability for identifying a significant value is less than 0.05. So in other words, the area is 0.05. This problem just asks us to do the same thing, but it says, okay, set it up so that you have boundaries. Again, dividing critical from non-critical. There's our boundaries. But the area is 0.01. So that moves the boundaries out further. So instead of being here, let me get this right. Instead of being where they are, gotta find my pointer. That's not my pointer. Hold on, there we go. Instead of being here, they're going to be farther out. Instead of being here, they're going to be farther out. So that's the setup for us. They want us to find those boundaries so that if we're beyond those boundaries, then we classify as being critical. Okay. So the setup, of course, is in our normal distribution. We have a mean of 22.7 and a standard deviation of 1.1 inches. How far out is this boundary? Okay. And how far out is this boundary? Now, by symmetry, those are going to be the same. So I think it's going to be easier and more direct to find that boundary. So the way we do that is we say, okay, we don't know what that value is, but we know what its x value or its z-score is because we can look that up in the table, right? We can look up the value for the z-score that has an area to the left of 0.01. And so if you look up in the table, the z-score that has the closest value is negative 2.33. All right. And so that's the z-score there. And of course, the z-score up here is 2.33. So those are the z-scores, but we need to convert them to their inches measurement. Okay. So we're going to use our little formula. Remember our formula that we use for z-scores. Looks like this. The z is equal to x minus mu over sigma. We know z. We can use either one at this point. Let's use the positive. Equals x minus x, which is unknown, minus 22.7 over 1.1. Right? And if we solve for that, right, if we solve for x at this point, right, by multiplying both sides by 1.1, and then by adding 27 plus 27 equals x, we get that x equals, not 27, 22.7, so I'll fix that. We're going to get x is 25.263. So that is the x label here. That is the boundary in inches that defines that upper boundary. So if we're higher than that, then we are considered to be statistically significant, different, right? If we get a measurement that is higher than 25.26, I guess we'd round that to 25.3. Then it's significant. Then I need to do the same for over here for this side, and we'll just set that up. It would look like this: negative 2.33 equals, again, the unknown x minus 22.7 over 1.1. And if you solve for that, you get this value. And so that'll give you your two critical values. That if you're beyond, then you are considered to be significant. If you're not, then it's not significant. All right, anyway, I hope that helps.